Hello, my name is Cornejo, and this is lab activity number 4 for EEE3303 Lab, electronics one. And the first part is halfway rectifier, well, parts 1 and 2 are halfway rectifier, but this is mainly focusing on the positive output. Here, voltage input is 5 volts peak to peak, frequency 60 hertz, and then the voltage peak only one is 2.5. Theoretical should be 2.5 minus 0.7. 0.7 is the voltage of the diode, so it should be around 1.8 volts peak. The output, we get 1.892, the measure result. And here is the simulation. Again, it shows only the positive peaks going out, the negatives are filtered and chunked to the ground. And here's a picture of the actual circuit itself that was used for the measurements. Here's the same experiment, but instead of the positive output on the peak waves, is the negative peak waves that are being output. Everything else remains the same. Simulation, multisim, same results. And then it comes out. Here's the circuit. Okay, so now for part 3, this is gonna be a bridge rectifier going down to the step down transformer. Voltage inputs 5 volts peak to peak, frequency is 60 hertz. In here, it reads in here 1.254 volts RMS, but it can be changed to 1.98 volts AC. In this case, the rectifier should cause a voltage drop of 2.2 volts because of each 0.7 voltage drop because of the diode. And interesting to note is that there's actually a DC offset of 1 volt in here, while the amplitude of the peaks alone is just averaged to around 0.641 volts. However, in the multi-stream result, there is actually no DC offset, it's just the peaks going. It's a positive peak output for each cycle. And here is the circuit itself, and there's a big transformer. Very hard to use. Very unconventional. It's too big. And this is part 4, but instead of rectifier, it's a center tap transformer. One thing that to know is that the voltage output, both in the simulated and experimental, is actually lower than the bridge rectifier voltage output. Here it is. There's no DC offset either on this one. It says the positive peaks. Not smooth as in here. In the simulation is very smooth, but the actual measure results is not that smooth. Well, here's the circuit itself. And here is it's just a simulation of a signal limiting circuit. In this case, I use input 10 volts. It's actually 10 volts RMS, not 10 volts peak to peak. Frequency is still 60 hertz, and what I wrote down here is R1 and D1 from a parallel positive limiter of positive bias. R1 and D1. The positive bias causes the diode only to refer bias when the input waveform exceeds 5 volts, so any voltage exceeding 5 volts is limited by being shunted to ground. So basically it's clipped off anything above 5 volts. And then R1 and D2, they form a parallel negative limiter with a negative bias. The negative bias causes the diode to only be forward biased when the input waveform exceeds the negative 7 volts. And again, so once again, anything above negative 7 volts is just clipped off because it's shunted to the ground. So the upper limit is 5 volts and the lower limit is negative 7 volts. And this was a voltage doubler. Currently it should output a DC voltage level. There's approximately twice the AC peak value. In this case, I use like 10 volts AC. So the output voltage doubler should be around 20, and it reads 19.487. So yeah, it's around 20 volts. Yeah, and what's down here, voltage doubler has 2 capacitors and 2 diodes. Each diode allows 1 capacitor to be charged in every alternate positive discharge using a cycle. The charging of the capacitors can be observed ultimately here. They are observed slowly charging up and ultimately causing a 20 volt output. A DC output, I should say. It's important to remember it's a DC output. Here, for part 7 is not a half-wave rectifier, but in this case we added a capacitor. You can see the capacitor's role is just to smooth out the pulsating DC circuit. The pulsating DC signals. We did this only with 0.1 microfarads capacitor. Similar result to multi-sim. The bottom is smoothed out. But here is a 1000 microfarads electrolytic capacitor, and it's just a straight DC signal, smooth and steady DC signal. It's around 3.8 volts DC output. Here's the same thing right there. There's a steady, smooth DC signal. Here's the both 1 microfarad, 0.1 microfarads capacitor, and then the 1000 microfarads capacitor. Pretty big, that one. And then for the final one is a senior diode voltage limiting circuit, but this was having trouble because my DAC only allows a maximum output current of around 2.3 milliamps. So all of the results is just like they change slightly. Like when the resistor gets larger, the resistor value for one gets larger, and the current decreases, as well as the voltage output. You can see in simulation. Simulation provides the results. You can see it definitely exceeds 2 milliamps. So this one is very hard to actually do on the MyDAC. And that's it for activity 4.